Good afternoon, everyone. I hope that you're having a good day so far and that everybody's doing fine. We're going to be looking today at lesson 30.09, which is exponential functions. We're going to be looking specifically at applications of exponential functions, and we're going to continue with this lesson on Friday. So this is just part A of the lesson. Since we've moved on to exponential functions, I guess it's the case that we are officially done with trigonometry. This lesson is on page 4 of your current lesson handout. We're going to start off with a definition of exponential functions. Exponential functions are functions that can be written in the form y is equal to some base raised to the power of x. And that base is a number. But we have restrictions on the number. If you take a look at what it says there, it says that the base has to be greater than 0. What is that telling us? It's telling us that you cannot have a base that's equal to 0 and you cannot have a base that's negative. There's another condition which says the base cannot be 1. So when we put this all together, what we're saying is the value of b has to be a positive number not equal to 1. Visually, what that looks like is b can be any number between 0 and 1, and it can be any number bigger than 1, but it can't be 1, it can't be 0, and it can't be negative. So those are the rules for b. And as we're going to learn very shortly, the value of b is going to tell us the shape of the exponential function and what's happening to the function as we move from left to right on the graph. The most important aspect of the exponential function is the base b. It's called the factor of change, and it's the number that the function is regularly multiplied by. Now, please remember that whenever we say function in mathematics in this context, we mean the value of y. So what I'm telling you is whatever b is, that number is what y gets regularly multiplied by. So if we had an exponential function that was y equals 4 raised to the x, where b was 4, that would mean that y is going to be multiplied by 4 on a regular basis. As a warm-up, in order to understand the role that b plays in the graph of an exponential function, we're asked to compare the two graphs, y equals 2 to the x and y equals 1/2 to the x. I'm going to use my graphing calculator for each of these, and of course you can follow along, but I want to point out to you that I've already entered in a particular window setting that is going to be best for my explanation here. My window setting is going from -2 to 4 for x, and I'm putting a mark on the graph every 1. That's what the x scale is. And for y min, I'm starting at 0 and going up to a maximum y of 16, again putting a tick every 1. And then I can go to y equals, and I can enter that first function, which is y equals 2 raised to the x, and we can take a peek at what the graph looks like. Now, I had told you that the base, which in this case is 2, tells you what is happening regularly to y. So I'm going to go to my table setup and just check. It says that I'm starting at 0 and I'm going up by 1, and it's all on automatic. So when I take a look at my table, look at what happens when I go from x equals 0 and I increase x by 1. When I increase x by 1, y gets doubled. It goes from 1 to 2. And when I increase x by 1 again, y continues to get doubled. It now is 4. And when I increase x by 1, y gets doubled again. So when you look at the left-hand column here, x is increasing by 1 on a regular basis, but what's happening to y is doubling on a regular basis. 1 times 2 is 2, times 2 is 4, times 2 is 8, on and on down the line. By the way, I could go back in the other direction and show you that at -1, the value of y is 0.5. It would have to be because when you double 0.5 moving forward, it would give you 1. So when we're talking about a graph changing, we always want to think of left to right. It's doubling, y is doubling as we go left to right. So I'm just going to take this graph and just drop it here where we can talk about it a little bit later. Now what I'm going to do is I'm going to graph y equals 1/2 to the x. I have the same window settings. I have the same table settings, but now I'm going to enter in for y 1/2 raised to the x. It's just as easy for me to put 0.5 raised to the x in there. Actually, I'm going to change the window settings slightly. I'm going to go from -4 to 2 this time. And when I take a look at the graph, it's pretty much a mirror image of the graph of 2 to the x. And if I were to go to my table, I'm going to actually scroll up in my table to get over here to -4. When x is -4 on this second graph, y is 16. When I add 1 to x becomes -3. What happens to y is multiplied by 0.5. And you can see that as we go to larger and larger values of x, every time x increases by 1, y is multiplied by a factor of 0.5. So we're asked to compare these two. I'd better just label them. This is the graph of the function y equals 2 raised to the x. This is the graph of the function y equals 0.5 raised to the x. And we're asked to do a comparison. So how are the graphs the same? Well, the y-intercepts are the same. They're both equal to 1. When we take a look at these graphs, they both cross the y-axis at 1. And the reason for that is a y-intercept is where x is 0, and if you evaluate 2 raised to the 0 or you evaluate 0.5 raised to the 0, you are still going to get the same answer. You will get 1. Another thing that these two graphs have in common is they have what's called a horizontal asymptote. So this line is called a horizontal asymptote. And what a horizontal asymptote is a line that the graph is going to get closer and closer to but never reach. If you were to follow the y equals 0.5 to the x, and you continued to go further and further to the right, that graph would get closer and closer and closer to that dotted line, but it would never reach that dotted line. The reason it's getting closer is y gets multiplied by 0.5 each time. So it's going to be cut in half and cut in half and cut in half. But the end result is, even if it's very, very close to that horizontal asymptote, when I cut that distance remaining in half, there's still some distance remaining. When we take a look at this other graph, we would have to go to the left. And the same kind of thing takes place. As you get further and further to the left, the graph will get closer and closer and closer to those asymptotes. And the equation of those asymptotes are both at y equals 0. So we can add that to our list of similarities of these two graphs. They have the same horizontal asymptotes. Which is y equals 0, or I could say the x-axis. There might be some other similarities, but I'm not too interested in writing them all down. They both have the same domain. The domain of each of those functions is x is any real number. Since they are entirely above the asymptote, the range of each of those functions would be y is greater than 0. But I'm not too concerned about that. I want to focus on how they're different, and they are different in a very, very fundamental way. When you take a look at the graph on the left, this is what's referred to as an increasing exponential function. And the graph on the right is referred to as a decreasing. When we use the words increasing and decreasing, it always is in reference to what's happening to y as we go from left to right. So when I look at left to right here on the graph of y equals 2 to the x, the graph takes off. It gets bigger and bigger. When I look at left to right for the graph of y equals 0.5 to the x, it keeps getting smaller, left to right. So that's the big difference here between these two functions, is that y equals 2 to the x is what we call an increasing exponential function, and y equals 0.5 raised to the x is a decreasing exponential function. That probably shouldn't come as a big shock to you, because I've already told you that the base is what happens to the function as you go from left to right. So if the base is 2, the function is doubling. If I give you an amount of money and then I double it and I double it and I double it, the amount of money you have is going to grow. It's increasing. If you take a look at y equals 0.5 to the x, b is 0.5, which means the function is being multiplied by 0.5 regularly, which means it's being cut in half. And if I have half of a cake being eaten, then I have less cake left over after it's eaten. And then if I eat half of whatever's left, I have even less. So every time I eat half of the remaining cake, there's less and less cake there, which means the amount of cake is decreasing. In terms of the mathematical properties of the graph, like domain and range and asymptotes and all that, I'm really not too concerned about that right now. We're going to need to refer back to these graphs later on when we learn about something called logarithms. But the key point I want to stress right now is this second one that you're looking at here. There are two types of exponential functions. Increasing exponential functions, which we can call growing exponential functions, and decreasing exponential functions, which we can call decaying exponential functions. Another good word instead of decaying is declining or shrinking. What we're looking at here is a picture from your textbook. This is a very basic picture of y equals b to the x as long as b is greater than 1. If b is greater than 1, then you are going to be referring to a function that is increasing. Because if b is, for example, 5, the function gets multiplied by 5 on a regular basis. Multiplying something by 5 makes it larger. Multiplying something by any number greater than 1 will increase the value of that thing. On the other hand, if you have a value of b that is somewhere between 0 and 1, like 1/2 was in our example, then it will be a decreasing function. As a quick illustration, if b was 0.25, then you're going to be multiplying the function regularly by 0.25, and that means it's going to get smaller and smaller and smaller. If we put this together, we can add something to that graphic I showed you earlier that showed the allowable values of b. And we can say that we know b has to be between 0 and 1 or greater than 1, but now we know that if it's between 0 and 1, it is a decreasing exponential function. But if it is greater than 1, it is an increasing exponential function. And what we want to focus on for the lesson today, really, is applications of increasing exponential functions and of decreasing exponential functions. And it turns out we have this formula. Y equals A multiplied by B raised to the T over P. And this formula is for any exponential growth or decay. There are a lot of things in our world that grow exponentially or that decrease exponentially. An example of exponential growth is the population of the planet Earth. Another example of exponential growth, although it's no longer exponential, is the number of people that were infected with the COVID-19 virus. About 3 weeks ago, if you were to plot the number of people as a function of the day, you would see that the number of infections as you went from one day to the next was being multiplied by something regularly. There are some things in our world that decline exponentially. I drive a 1999 Dodge Dakota truck, and I bought it in 1998, and I think I paid about $34,000 for it. And every year I drove it, the value of the vehicle decreased and decreased and decreased. And it turns out it decreases according to an exponential formula. So all exponential growth and decay can be modeled with this formula. The first thing I want you to understand, I really think this is important, is that this formula has a total of 5 letters in it, but it is very important for you to understand that 2 of the letters are what we refer to as variables. The variables are Y and T. The other letters, A, B, and P, are best called constants, or we can call them parameters. So the value of A, B, and P, when I start talking about what my truck is worth from year to year, are going to be different numbers than the values of A, B, and P when I talk about the population of the planet Earth. Each different situation has a different set of parameters. So Y and T are the variables. What are the parameters A, B, and P? Well, A is the initial amount. So whatever the initial amount that you're modeling is equal to, that's A. In the example of my truck, the initial amount A would have been $34,000 because I believe that's what I spent for it. That's what it was worth. B is the factor by which things are changing regularly. So I will tell you right now that for about the first 15 years of earning a vehicle, the value of B is 0.8, which means that every year you drive it, the new value at the end of the year is only worth 80% of what it was at the beginning of the year. So each year it gets multiplied by 0.8. P is the period of time required for the quantity to change by that factor. So that's going to depend on the situation, but if I told you that my truck only kept 80% of its value every year, the period would be 1 year. But we'll look at specific examples in a second. In fact, let's take a look at a specific example right now. The number of bacteria in a sample is originally 1,200, and the bacteria double every 8 minutes. What we're looking at modeling here is a function where on the horizontal axis we have time, and on the vertical axis we have the number of bacteria. We always use Y for the vertical axis and time for the horizontal. So Y is the number of bacteria. Now, what are our parameters equal to? We're asked to determine the equation describing the population of bacteria as a function of time. So we're going to be using this formula that I have highlighted here because it can be used for any exponential growth or decay. But if we're going to use that formula, we need to know the values of A, B, and P. So what is A equal to? Well, A is the initial population of bacteria, which would be 1,200. B is the factor by which the bacteria is changing. Well, if you're told that something doubles, that means it's being multiplied by 2. And it happens every 8 minutes. And all we are going to do is load those three parameters into the equation y equals a multiplied by b raised to the t over p. So we are going to get y equals 1200, that's my a value, multiplied by 2 raised to the t over 8. B is 2 and p is 8. That is the answer to question A. And that is what we are going to use to answer questions B and C. All right, question B asks us to find out how many bacteria will be present after 1 hour. Now, when you take a look at all of the information in the question, it was doubling every 8 minutes. And what that means is our time has to be in minutes. When we talk about 1 hour, everybody should know that 1 hour is 60 minutes. And if we know that y is equal to 1200 multiplied by 2 to the t over 8, all we have to do to calculate the answer here is put 60 in for t. What will we get? We're going to have y equals 1200 multiplied by 2 raised to the 60 over 8. I probably wouldn't put this all into my calculator at once. I would probably just take 60 divided by 8. Then I would take 2 raised to that, and then I would multiply by 1200. So after 1 hour, there are 217,223 bacteria according to this model. Take a look at C. How long will it take for the population to reach 5 million? Well, what happens now is we take this formula that we have, and this time we know y. Y is 5 million. So we can put 5 million in for y and have the following equation to solve. Unfortunately for you, you don't know how to solve that equation yet. In order to solve for an exponent, you would need to know something about logarithms. So there's no algebraic way for you to solve this problem, but what we can do is take the left side and equate it to y1, and take the right side and equate it to y2, and find out where these two are equal. And wherever they cross, that will be the time. In other words, everybody, we're solving question C graphically. The most tricky part about this is finding the right window setting so that you can see where the graphs intersect, but we'll get to that. So my first y is 5 million, and my second y is 1200 multiplied by 2 raised to, we need to put a set of brackets here now, t, which is x, divided by 8. Now we have to set up window settings so that we'll see the graph. You cannot just keep trying zoom out, zoom out, zoom out. It won't work. It will just cause frustration. The first thing to note is that if we want to see y equals 5 million, then in our window settings, we have to go up to at least 5 million. Now, I don't want 5 million to be right at the top of my screen, so I might go up to 6 million. For the scale, it doesn't really matter. I'll put a tick every 1 million. Now, how do I determine my x? We're always going to start with these applications at x equals 0. One of the things I can do is use my table. So I'm not going to worry about the graph right now. I'm going to go into table setup. Notice that I can start at 0 and go up by 1. If I look at my table now, here's my y1, which is 5 million. Here's my y2, which I want to reach 5 million. And I can see that, oh man, I'd be scrolling down for a fairly long time to reach 5 million. So maybe what I should do in my window settings is start at 0 and go up by 10. I'm using my table to explore when it's going to reach 5 million approximately. So now when I go to my table and I scroll over, I can see, well, we're getting there actually. We're getting some pretty big numbers here. In fact, I think this is over 16 million. That tells me that if I go up to x equals 100, that will pass 5 million, and I should be able to see where they intersect. Now, if I didn't reach 5 million right away, I would have gone back into my table set and maybe gone up by 20 or 30 or 100. But using my table, I can see that if I go up to 100 for x, that should be sufficient to find out where they intersect. There's the 5 million. And there's the 1200 times 2 to the t over 8. So to find the intersection point, you go to your calculate menu, which is second trace. You choose intersect. And I've told you this in class before, as long as you only have two functions that you're looking at, all you have to do at this point is go enter, enter, enter. Calculator grinds away for a minute or so, and you get 96.2. So how long will it take for the population to reach 5 million? 96 minutes, rounded to the nearest minute. Let's take a look at another one. This one deals with what's called a radioactive sample, which has something called a half-life. And you're told here that a half-life of 15 days means that every 15 days, 1/2 decays. It turns into something else. You don't need to understand the physics of that, but you do need to understand that the amount of radium is being multiplied by 0.5 every 15 days. That tells us that P is 15 days. And the base, which is the factor of change, is 0.5. And then it says if the sample starts with 100%, well, that's the initial amount then, 100%. What is the formula or equation that describes the amount of radium, that's our y variable, as a function of time, that's t. We load everything into y equals a times b to the t over p. That's all we need to do here. We will have the amount of radium remaining equals a, which is 100%, times b, which is 0.5, raised to the t over 15. And that's our answer to question A. And I think you know where this is going. We're going to use that equation to answer questions B and C. What does B ask? What is the percentage remaining after 80 days? This is a case where we're just going to take the equation and replace t with 80 and simply do a calculation. We can take 80 divided by 15, take that as a power of 0.5, and then multiply by 100. So 80 divided by 15 gives me this number. I have to take 0.5 and raise it to that exponent. Then I need to multiply by 100. The answer to question B is after 80 days, there is only 2.48% remaining. If we take a look at C, C says that the percent remaining has to drop to 1% before it's safe to handle. The question is, how long is it going to take for it to be safe to handle? This time what we're doing is we're putting 1% in for y and we need to find out the value of t that makes that true. Once again, if you know y and you're trying to find t, you don't know how to do that on paper. You must use a graphical approach. This will be y1. This will be y2. And we are interested in, of course, where they are equal. We're not going to have to mess around with the window settings as much for this because the numbers are smaller. y1 is 1. y2 is 100 multiplied by 0.5 raised to, in brackets, x divided by 15. So what are my window settings going to look like? Well, if I start off with 100% for y, and it's a decreasing function, that means my y min can potentially get closer and closer to 0. I'm going to go from 0 to 100 for y, and we will go in increments of 10. Now, what am I going to put for x? Well, we could go to our table again and try to find out. If I go to my table and I start off at 0 and go up by 1, and I look at my table, don't forget, I want y2 to reach 1%. Well, I have a feeling I'm going to be in for a bit of scrolling here, but I'm not going anywhere, so I'm just going to keep going. I can see that it's getting to be around 20% after 36 days. This is a very tedious thing, but I just want to show you that even if push came to shove, you could start doing something like this and saying, well, it's getting closer and closer around 70 days. So maybe if I went to 100 days, that would be enough. The beautiful thing about this is if I go to 100 days and it isn't enough, I can just go back in here and go to 150. I don't know, let's check it out. By the way, that thick line you see at the bottom is y equals 1. So I am guessing, everybody, that there is a point of intersection of the line y equals 1 and the curve someplace in this area. All I have to do to find it is go to my calculate menu and choose intersect. And by the way, there's only 2 functions. I just hit enter 3 times. If I get an error, then that's telling me that the point of intersection isn't visible, so I might have to go up past 100 days. But I have a feeling we'll see it here. 99.7 days, so it's just under 100 days. So 99.7 days is the answer. All right, we have one more example to do. Example 3 tells us that we have 2 towns, Allentown and Brementown. Now, Allentown has a population of 75,000, and its population is decreasing at 5% per annum. Annum means year. It's where we get the word annual from. The population of Brementown is only 10,000, but it's increasing at 9% per annum per year. So Allentown's population is declining exponentially, and Brementown's is increasing exponentially. What are the exponential functions for the populations of each town? I'm not going to use y. I'm going to use different letters for the population. So when I talk about Allentown's population, and then I talk about Brementown's population, the variables I'm going to use will be A and B. So A is the population of Allentown, B is the population of Brementown. Now what are the values of the parameters? Little a is the initial population of Allentown, which is 75,000. P is the length of time it takes for the change to happen, and that's going to be 1 year, because it says that the population decreases at 5% per year. If we jump over to Brementown, Brementown has an initial population of 10,000, and the period of change for it is also 1 year. We just need to discuss how we find B for each of these. And this is the only reason why I'm including a third example. If there was something that you wanted to buy in a store, forget about populations, there's something that you want to buy in a store. I don't know what it is, but you're really excited about buying it. And it has a regular price. It has an initial price. And it is on sale for 5% off. So now there's a new price for this thing. Well, the new price will be 5% less than the original price, which means the new price is going to be 95% of the initial price. What I'm telling you is to go from something to 5% less than that thing involves multiplying by 0.95. You can try this if you like. Take an amount of money, find out what 5% of that amount of money is, subtract it from the amount of money, then go back to the beginning and just find out what 0.95 of the original amount is, and you will discover it's the result after removing 5%. After all, this is 95%. We're losing 5%. We started off with 100%. If you have 100% and you lose 5%, then you have 95% left. What I'm getting at is the value of B for Allentown is 0.95. The value of B for Brementown is going to be 1.09 because you start off with 100% of the population and you gain 9%. And 100% plus 9% is 1.09. And now we can answer question A, which is, what are the exponential functions? The population of Allentown is the initial population multiplied by the factor of change, which is 0.95, raised to the t over p, but p is 1, so it's just raised to the t. The population of Brementown is the initial population multiplied by the factor of change, which is the value of lowercase b, raised to the t over p, but again, since p is 1, we don't need to worry about putting it over 1. We can just write 10,000 times 1.09 to the t. That's the answer to question A. Question B says, how many complete years of population change will it take for the population of Brementown to exceed the population of Allentown? If I were to plot Allentown's population here, Allentown starts off at 75,000 and it declines exponentially. So the red curve is Allentown. On the other hand, Brementown starts off with only 10,000 and it grows exponentially. So the blue graph is Brementown. What this question is asking us to determine is where Brementown first passes Allentown. The bottom line here is we can sketch these two functions. Allentown's was y equals 75,000 multiplied by 0.95 raised to the t. Brementown's population function was 10,000 multiplied by 1.09 raised to the t. I'd better just go back and check those. I think they're right, but they're okay. So we want to know where they intersect. We're simply going to graph one of these as y1 and the other one as y2. $10,000 multiplied by 1.09 raised to the x, and 75,000 multiplied by 0.95 raised to the x. For my window settings for y, I guess I'm going to have to, if I want to see all of the important features, go up to about 100,000 because the graph of Allentown starts at 75,000. So I'm just going up to 100,000 so I can see that. I don't know what kind of scale I want. I guess I could go up by increments of 10,000. This is just where it's going to put the ticks. Now, what am I going to put for my domain settings? Well, I could go to my table of values again. This is a very useful idea. Now, I'm way at 64 years, so I'm going to set up my table again to start at 0 and go up by 1. This is going to give me an idea, and in fact, we could answer the question just by looking at this. I want the number in y2 to be smaller than the number in y1. y1 is Brementown, and it's getting closer and closer to the population of Allentown. And right there, we've got the answer, actually. You know what, everybody? The answer is 15 complete years. Because at 14 years, Brementown is only at 34,400 people, and Allentown is at 36,600. Allentown is still winning the population race at 14 years. But at the 15th year, after 15 years of change, Brementown has finally surpassed Allentown. So the answer to the question is 15 years. If we wanted to know a more precise answer, we could go to our window settings and go up to, say, 20 years for x. Now that we know the answer is around 15, graph, we should see two functions. Here comes Brementown. Population is growing, growing, growing. And here comes Allentown. They're losing people. I can go to my calculate menu and choose intersect. And the answer is 14.66. But again, the question said how many complete years would it take for Brementown to first surpass Allentown? So you have to round up no matter what. Even if this number was 14.02, the answer would be 15. So we've got an answer now, 15 years. And we're done. What we're going to do next time is apply this formula that we've been using, A times B to the T over P equals Y, to money. On the next page of your handout, there are 5 questions. They deal with population growth, bacteria, radioactive decay. Those are the 5 questions I would like you to try for next time. And next time we're going to be applying this to money. I hope that lesson made sense to you, and I hope you have a great rest of the day. Don't forget that tomorrow is a Google Meet day, so if you do need extra help, by all means stop by, and I'm more than happy to provide that help to you. Have a wonderful rest of the day, you guys. We'll talk to you later.